So a lot of functions of the Brownian motion turn out to be martingales. So we know that the standard Brownian motion is a martingale because we've just shown in the previous clip that a Brownian motion starting at any x and having any volatility sigma is indeed a martingale. And the standard Brownian motion starts at 0 and has volatility 1, so it qualifies. So here we're looking at, a different process m, but before that, let's just look at something, maybe slightly simpler. Let's look at the quadratic function of the Brownian motion. So namely, let's look at the Brownian motion squared. And so how do we think about this? What do we expect this process to do on average? Well, we probably are thinking that it's going to increase over time. It's certainly never going to dip below 0. And it's kind of, in a sense, you can think about it as taking all the probability mass where the Brownian motion is negative, and because of the squaring part, it kind of pushes all that probability mass upwards, giving us the intuition that this process is going to increase on average. The variance or standard deviation of the Brownian motion will increase, and we're squaring it, moving it up, above the x axis. And so this, b squared would likely not be a martingale in that case. We'll show a related calculation to verify that in a few minutes, but the idea is that if we buy something at this price here, we're very likely going to see a profit by time t. So this would be our profit buying at time s and selling at time t. And this, here this is just a single example of a path, but on average this seems like it's going to give an expected value that's positive. And so here, when I've kind of written down this m here, I've taken this increasing tendency of b and tried to counteract it by another function. So I needed something that kind of grows linearly and or quadratic, just something that increases. And I've chosen a linear function. So this is a function of slope minus t. This is a line f of t minus t. And so when you subtract them, when you superimpose these two, I guess here you add these two functions together, and over there you're just subtracting a t. It's the same thing. We're hoping to get something that will kind of stay around the same value, so that the expectation of the future, is basically wherever we are now. So first things first, don't forget to verify integrability. We want to look at the absolute value and see that its expectation is finite at every point in time. So here I would just use the triangle inequality. You have a difference of b squared and t that's going to be bounded above by b squared of t plus t. That bounds the absolute value of the difference. And what's this? This is just the variance of the Brownian motion. Just a normal, this is mean 0 with variance t, right? That's the normal distribution of the Brownian motion at t. And so you just pick up a 2t here, less than infinity. So variance of the Brownian motion at time t plus t gives you a finite value. And this should be finite for every value of t, which it is. So clearly this is increasing, but that's okay. We just don't want it to diverge. So the next part, is kind of the main property of the martingale, that we can't, the best prediction of the future is the current value. And in the first step, I'm applying a Markov property to get rid of the entire history of the path, just to make things a bit simpler. And you can kind of think through why this is the case. This would be a way to verify the Markov property for any function g of a Brownian motion. Basically one way you could do this is, if you want to work this out kind of as a separate exercise, is to think of applying the tower property here. So I want to start off here and I want to get to this place. How would I do it? You could either do it on the level of expectation or convert to a conditional. You can do it as a probability or convert this to a conditional expectation, and then use the tower property to condition on the entire path of b. If you know the entire path of B, then you know the entire path of G of B, and then after that, you know exactly that B is a Markov process, and knowing its entire history before time s won't help you carry out the computation of this probability. Only the value of B at time s is important, and then the tower property would collapse again, and you'll see that you get this conditional probability here, verifying that any function of a Brownian motion is indeed Markov. And so that's just a long-winded way of saying that as we expect, M is going to be Markov, and we can switch to this step here. We could have done this a different way and just kind of carried on, so I actually didn't need to fill in this step to get to the next line. We still could have kind of carried this a large conditioning random variable with us, and we would have lost it later with a slightly different argument. But once you have something like this, the trick to use is to subtract and add what you want. What do we want? We want this to be the prediction. The prediction of the future at the current value should be the current value if we want to have a martingale property. And now we're hoping that the remainder just integrates out to 0. So we want this to go to 0. Hopefully that happens, and that will establish, that will leave this term establishing the Markov property. So the only thing I've done, again, to go from this line to this line is add an MS and subtract one, and it comes in and out of the expectation because it is known. We're conditioning on that value. So let's see what I did in the next step. I just used the definition of M to pick up a T minus S term. It's subtracted because T was leading, and then what I have is difference of these squares of the Brownian motion. And there's a couple of different approaches. There's a difficult route and an easy route, or I guess a semi-easy route. Let's talk a little bit about maybe the wrong way to go, or the more difficult way to go. So the first thing to notice is that I guess this would be BS. So one thing that happens is that by linearity of expectation, you get two terms here, and this one, you can kind of convince yourself that when MS is known, then BS is known, and vice versa. And so, when I've kind of pulled the expectation through around this term right here, I would have picked up the same Brownian motion at time s. So it's known and comes out of the expectation. And the second one has the Brownian motion at time t, conditioned on BS. Again, given MS, you know the value of BS, and given BS, you know the value of MS. So, now it's sort of like this part is left to compute, and, here, again, I'm kind of continuing and writing it as this integral against the transition density. This is our normal distribution, which has variance. In this case, it's sigma is not there, sigma is 1, but the elapsed interval is t minus s, so we have a normal density with variance t minus s, and it's centered at x, or no, is it centered at x? I guess in here it's not even, yeah, it's centered at wherever BS was. So if we're transitioning from BS to BT, so I've just denoted here a shorthand the location of the Brownian motion at time s as x. You can safely put Brownian motion, you can plug in BS here if that's easier, whichever way makes sense to you. But the idea is that at time s, the Brownian motion was, say, in state x. We've conditioned on it, so we know it. I could just substitute any letter for it. And here I'm integrating over all possible values in the future, dy, and of course this is my integrand, the random variable squared. And again, this is a normal density with variance t minus s and mean x, right? Our transition probability function for the Brownian motion. That's exactly what's being used here. And this integral will be pretty difficult. Could be difficult to compute. Could be a good exercise to try, though. What you're hopefully going to get out of this is something that cancels out all of these various parts. So you're gonna hopefully get, pick up a minus bs squared and, plus ts, but it could be some work. So probably good practice, but could also be a little bit challenging. Another thing to observe here is we talked about the transition probability for b squared. You can kind of see how you could come up with that. The transition probability for b squared would essentially be, or I guess what I meant is the distribution or the probability density of b squared at time t. You can exactly get this from from this expression here. So let's come back to the easy way. What's the easy way to carry out this, or an easier way to carry out this calculation? The first thing you want to notice is that bt minus bs factors like so. So these two products of the difference and the sum will just give you bt squared minus bs. So that's the first thing, and the reason for writing this is really just to get a handle on the increments. This independence of increments property is pretty useful. So I got one increment here, and this part doesn't really look like an increment, so I'm going to try to turn it into one. Here I've subtracted and added an s, so you have one increment here. That's the same one that stayed there. And here I've picked up an increment by subtracting an s and then added an s on this, to this term. So nothing has really changed going from here to here, but I am writing things closer to or I guess in terms of a function of the increments. So now you multiply things out. This increment times itself will give you that squared, and the other one will leave the increment and leave a factor 2b, which we know we're conditioning on bs, so 2bs will come out. So this is, that's why this is here. It's known, so it comes out of the expectation, and the increment itself that multiplied the 2bs is here, and its expectation is 0. So why is it 0? First of all, it's conditioned, so you want to be careful, but it is again an independence of increments property. This increment is independent of this one. These two random variables are independent, and so the expectation of this, given something that's independent of it, is just the expectation of the original random variable, this increment. The increment is mean 0, and so this expectation has 0 mean. On this side, similar type of idea, except that now the integrand is, or the thing we're taking the expectation of, is the increment squared. It's still independent of what's being conditioned here. bs minus b0 is just bs, so I just wrote it as an increment, but it's the same bs that was given. So now this is again independent of that, and therefore equal to this expectation, and that's that right there is the variance of an increment of the Brownian motion, which is t minus s. The volatility is 0. So what happens in the end, this t minus s comes out and cancels that one, and that was basically the result of evaluating this term. So this term is replaced by t minus s, which cancels this t minus s, leaving us with an m minus s, and the answer to this question is affirmative. M is indeed a martingale. So this is basically the the kind of the approach to verifying sort of all of them, whether you have a geometric Brownian motion is covered in Ross. These are the kind of the steps you wanna take. First, verify integrability, then start by stating this martingale condition that talks about what's the best prediction at a future time, and then try to get kind of add or subtract what you need. Sometimes you may want to divide or multiply to get the right kind of the right arithmetic to work for you, but the basic kind of approach is is illustrated well here.